Welcome to Massive Open Online course on chemical process intensification. This is module optimization for process intensification. It's module 5 and the lecture is 2 under this module, and in this module there is optimization algorithms to be discussed. So, this lecture includes the optimization algorithms for process intensification. In the previous lecture, under this optimization techniques, we have discussed some introduction regarding that different types of optimization and how that optimizations can be implemented. And here in this lecture, we will try to discuss something about that, what are the different algorithms that are being used for that optimization techniques for the process intensification. Now, as you know that there are several different types of that algorithms that are being used for optimization. Here mainly we can classify these algorithms into two divisions, like one is called evolutionary algorithms and another is called classical algorithms. And these two algorithms are actually coming under that stochastic algorithms. And in this case, let us have some look of these evolutionary algorithms and also classical algorithms there. So, in this lecture we are having these evolutionary algorithms where it is actually seen as a process of adaptation, that that as like that creatures are being evaluated adapting with the nature. So, here again that algorithms is actually created based on that adaptation of the process and based on which the algorithms is being actually procured. Now, in this case, if we actually supply a quality function or consider a quality function to be maximized, then one can randomly actually create a set of solutions there, and that is elements of the functions domain, and apply the quality function as an abstract fitness measure, like as an example the higher the better. So, this is the actually the concept of that evolutionary algorithms there. We are always that preferring that better one will be higher. So, in that direction, this actually in a particular functions domain and also based on the quality function that is being fitted for the optimal solution. So, in that case that depends on the selection of the function, that quality of a function that would be maximized just by creating a set of solution there. And in that case, elements of that function domain and the quality function to be selected based on that the process criteria, even some different variables that are actually involved in the particular processes for the process based on that process intensification. Now, actually these evolutionary algorithms are actually seems to be a very powerful tool to tackle actually the mono and multi-objective problems in the process intensification. And these are actually based on an imitation of the evolutionary principles of nature in order to reach that optimal solutions. So, we can say that that is why this evolutionary algorithms have been used to solve different problems, to solve that complex problems also in industry and services, in areas ranging from finance to production, management, and also in engineering field. So, the problems consider single and multi objectives, and there will be a certain constraints in most of the cases based on the process variables, even some process conditions. So, that is why these evolutionary algorithms are mostly used in several sectors like industry, engineering, and other that finance also department they are using this evolutionary algorithms there. What are the steps of that evolutionary algorithms? You will see that an evolutionary algorithms contains this following steps here, like initiation, then selection based on that mutation and crossover, because based on the crossover some mutation also depends, and once this mutation obtained, then how it can be selected, that also important. So, after initiation and then selection should be there. After selection, then you have to have some termination steps. So, these steps actually is correspond roughly to a particular facet of natural selection, and provide easy ways to modularize implementations of the algorithm category. So, that is why these steps are actually preliminary, that based on which that evolutionary algorithms are procured. Now, there are another method, it is called classical methods. Then in this case, that these classical methods actually address the multi-objective problem, that making a single objective problem there. So, a lot of multi-objective problems will be making a single objective problems. So, in that case, main objective is to generate a Pareto optimal. So, that is why classical methods will address the multi-objective problem, which will be actually a ultimate that single objective problem there. And evolutionary algorithms considers a set of solution instead of single one there, whereas this classical methods there it will generate that multi-objective problem making a single objective problems. Now, what are the approaches for the classical methods? There are two generally methods or approaches for the classical methods. One is to consider the optimization of an objective, while the rest of them are treated as the restrictions there. And the other approaches is performing a weighted sum of the different objectives by actually grouping them into a single function. So, if there is that different objectives are coming, so you have to group them, and you have to consider a single function based on that grouping. So, that is why these two actually approach is very important to actually execute these classical methods there. And so, in this case you have to consider that of an objective first, optimization of an objective, and rest of them are will be treated as that restrictions there. So, this is the first approach, and then other approach is that you have to perform a weighted sum of the different objectives by grouping them into a single function. Now, why evolutionary algorithms is well suited, that is also important to know here, because that their capability to evolve a set of non-dominated solutions that is distributed along with the Pareto front. So, in this case that whenever you are selecting some set of that objective functions there, and in that case based on that different objective functions, which one will be that actually feasible, and that capable of that feasible that set of that functions, and it should be it will have that non-dominated solutions, and it will distribute it along the Pareto front there. So, that is why it is actually these algorithms are being recognized to well suited for multi-objective optimization. And also this evolutionary algorithms it has some ability of such cases that where it can find multiple optimal solutions in one single solution, that will run evolutionary algorithms that is unique in solving multi-objective optimization problems. So, that is why it is very important. So, under this evolutionary algorithm, there are several different types of algorithms. Now, genetic algorithms are one of the most popular and useful optimization techniques for this kind of strategies among the evolutionary algorithms. And the representative technique of this evolutionary strategies which are really inspired by the nature as per that genetic algorithms. And in these genetic algorithms actually first proposed by that Holland in 1975, and they actually proposed that this genetic algorithm will mimics the process of natural selection. And in this algorithm the decision variables are to be codified to actually constitute a chromosome there. So, based on that this actually algorithms are being considered, where that how that that chromosomes is being constituted. And there are different kinds of codifications actually, being the binary one and the most popular in that case, because we are having that different kinds of codifications there. So, in that case binary one will be the most popular there. Other different types of course will be there. Now, what is actually that philosophy of that genetic algorithms, from where actually it has come? Now, if we start it from an initial that encoded solution, an entire population is generated based on this algorithm. So, we are encoding a solution like that, that total population will be generated based on these algorithms there. So, in that case this population is evaluated according to its fitness function, which you can say that it will emulate the survival capacity of the species there. So, that is why you have to select that fitness function where it will say that okay, there will be some survival capacity of the species or entities which are actually created that population there. And based on that value of the fitness function, that individual that is species should be sorted and also selected and actually to have a superior, or you can say that to have a well being which will become the parents of the next generation there. So, that is why based on the value of the fitness function, that you have to identify individuals, and it will be that sorted among all that species or entities, and then you have to select in such a way that that selection to become the parents of the next generation there. And then after selection, that the selected parents are actually combined to generate a new generation of the children. So, which partially replace the current population basis. So, this is simply that that finding out the better to better than best, like this. So, that is why the selected parents are combined to generate a new generation of children, and then after that this will partially replace the current population basis based on that survival or you can that fitness of that function. Now, children are that later mutated, and in order to ensure getting trapped in a local optimum. So, you have to make a set of that optimal solution where that children are to be mutated. So, after that mutating, you have to ensure that you are getting that trapped in a local optimum. So, in that case you have to select some that elitism operator which will allow you keeping the best solution during the optimization process, and then the entire population will involve for that that trapping in a local optimum, and which will evolve so the fitness improving over the generation there. Now, what are the techniques actually to solve these multi-objective optimization problems using the genetic algorithm? Now, there are several that techniques are available, like vector evaluated genetic algorithm, multi-objective genetic algorithm, even non-dominated sorting genetic algorithm, and next Pareto genetic algorithm, NPGA it is called, and also this non-dominated sorting genetic algorithm. This is actually very important and most popular, and also this is very easy to implement to get that optimal solution of the multi-objective optimization problems. And also another important one, it is called microgenetic algorithm nowadays are coming, but among these different techniques here, non-dominated sorting genetic algorithms are the most and easy to implement. Now, what are these actually non-dominated sorting genetic algorithm? It is actually denoted by NSGA2. It is a multi-objective genetic algorithm with that low computational requirements, even that elitist approach, also the parameters less sharing approach with respect to NSGA, and also it is the most used of multi-objective genetic algorithm, and it is usually taken as that reference when you are actually devising a new algorithms and which will be presented for that optimization problem. Also, we will say these algorithms builds based on the population of competing individuals, ranks, and also each individual is sorted according to non-domination level. So, the algorithm applies evolutionary operations to create a new pool of offspring, and also this algorithm combine the parents and offspring before that partitioning or you can call portioning the new combined pool into the fronts. So, that is why that this algorithm based on the competing individuals, ranks, and also sorted out of that each individual based on the non-dominated level. And also it is actually creating a new pool of offspring, and whenever you are just going to combine these parents and offspring, then you can combine a new actually pool into the fronts of that Pareto, where that you can get that optimal set of solutions there. Now, new algorithm inspired by nature like genetic algorithm. There are several other different types of that under this genetic algorithm. One is important, that is called Metaheuristic algorithm. In this case, it is an algorithm designed to solve approximately a wide range of hard optimization problems without having to deeply adapt to that is problem there. And also this type of algorithms are characterized because they are inspired by the nature, using stochastic elements, even have various that parameters that must be tuned for the problem. And there are two stages of that meta-heuristic algorithms, like that diversification and exploitation stages. A meta-heuristic depends on appropriate balance between diversification and exploitation stages. The diversification stage allows you to explore a large part of search space, while the exploitation stage concentrates the efforts on those areas of the search space which are more, in this case, promising there. And also if a meta-heuristic algorithms gives more weight to diversification, then you may not get the close to the global optimization solution. So, but in that case, if more weight is given to exploitation, then you can have a fall into a local optimum solution. So, the most popular and used meta-heuristic algorithms are, in that case, simulated annealing, taboo search, differential evaluation, and colony and particle swarm optimization. Now, what is that simulated annealing optimization algorithm? So, it is an optimization technique that is inspired by the process of annealing of metals. In this process, first the metal is heated by raising the energy of the molecules and then allowing them to move freely. After that, a cooling process is performed which minimizes the energy of the particles by their accommodation in a crystalline structure. So, that is why you will see that if the cooling is done very quickly there, then an amorphous structure is obtained which leads to a higher energy state. So, this is called annealing. So, this concept of annealing of the metals, the algorithms is actually procured, or you can say that optimization is made. So, that is why this is based on the that how metal is heated by raising the energy of the molecules and allowing them to move freely, and also cooling process, how that minimizes the energy of the particles by their accommodation in a crystalline structure, and also how quickly then an amorphous structure is obtained and which will leads a higher energy state. In this case, that Kirkpatrick et al. And Charney 1985 has pointed out that this analogy between this process and the optimization strategies, like the objective function is represented by the energy of the particles, while the temperatures and the cooling path are the operators here. So, very interesting that energy of the particles here, where that based on that energy that annealing of the metals are being happened. So, in that case the objective function will be considered the energy of the particles, where the temperature and the cooling path will be considered as a operators. So, unlike this genetic algorithm, this simulated annealing does not use that populations, but instead it uses only one solution, thereby the acceptance new individual is based on a probability value. So, that is why in this case this annealing optimization algorithm does not require any population, whereas this that genetic algorithms they are it requires in that case that population based. In this case also annealing uses only one solution, thereby the acceptance of this new individual is based on a probability value is very important for this consideration of this algorithm. Now, a different approaches for simulated annealing is the many authors have proposed different approaches to use simulated annealing for multi-objective problems, such as that L infinity Sevier norm, even weighted sum of probabilities for all objectives for a single evaluation or single solution and entire populations, and also Pareto dominance is there, normalized aggregation functions to be considered here there. So, these are the different approaches for this having of solution by the simulated annealing. And tabu search is the algorithm where it is proposed by this is Glover. Based on this algorithm, a unique solution is evolved through admissible movements that allow you decreasing or not the objective here in case of minimization in this case. So, in this case remember that reverse movement are not allowed in order to avoid falling in a local optimal solution there. So, that is why this algorithm will give you that unique solution through the admissible movements, and which will allow the decreasing or not the objective in this case. So, reverse movements are not sometimes allowed in order to avoid the falling in a local optimum value. And to register the information about these optimal points, different that memory arrays as an operators are to be considered or used, and in this case the main operators are generally three kinds of memory arrays are considered. One is short term, another is immediate, intermediate term, and then long term. And these memories register the information about recent visited points and optimal or near optimal points, and also it will explore to the regions accordingly. The ant colony is developed by Marco Dorigo, that is inspired by colonies of real ants. In this case that real colonies, the ants secrete a chemical substance called pheromone, which is used to communicate between them. And also in this case the ants tend to take the paths where large amounts of pheromone are present there. So, in this case you will see that at the beginning of the searching process all the ants are dispersed looking for food, and as the optimization process if it is progressed, then ants begins to follow a common path, the one with higher levels of pheromones, and also in the end the whole colony follows the same path which is the shortest there, and also several multi-objective approaches have been developed in order to use ant colony for this kind of problems as per literature we are having there. Now, what are the differential that evaluation? The differential evaluation is a metaheuristic evaluation which is proposed by Price and Stone in 2005, and it is generally developed for the continuous optimization, and it shares some similarities with traditional evolutionary algorithms, and also it is not giving the means for using that binary solution according to a simple genetic algorithm there. and also it does not use a probability density function to self adapt its parameters as an evaluation strategy. And also several variants of the differential evaluation algorithms are to be considered, and which is possible they are depending on the type of selection, the recombination, and also the mutation operators. And particle swarm optimization, that is proposed by Kennedy and Eberhard in 1995 there, and according to this approach you can say that the use of flying potential solutions through the hyperspace generally used for accelerating that convergence there, and in that case you have to measure the performance with a function that will be very similar to the fitness function. So, that is why the strategy should be similar to the evolutionary algorithm, and that is why this approach giving the use of flying potential solutions to the hyperspace, and by generating that accelerated that convergence. Now, let us have some look of process synthesis intensification, some algorithms there. Now, in this case Babu et al 2015 they have given different types of algorithms and also they are that different sets for that algorithms which are being applicable actually for the process synthesis intensification. Now, in this case if we apply this process synthesis intensification, of course this one framework is required. Now, this framework requires the use of different algorithms like this. These algorithms can be grouped into two sets like set 1 and set 2. So, in this case set 1 generally correspond to algorithms that are needed to decompose the problem from the largest scale, that is called unit operation, to the smallest scale, that is called phenomena. So, very important that unit operation to the phenomena scale to be considered in the first set. And in the second set they told that this corresponds to those that are needed to aggregate from the smallest scale to the largest scale there. So, this is here very interesting that this one is going from that the smallest scale to the largest scale, where in the set 1 in this case that decomposing the problem from the largest scale to the smallest scale there. And sub algorithms also set 1 and set 2 are there. So, in this case some sub algorithm of set 1 are being given here that is in table in the slides, like sub algorithm here algorithm 1.1 that is set under this that is 1, and to transform a base case flow sheet into a task based flow sheet, then you have to consider this sub algorithm there. This is actually under this objective to transform a base case flow sheet into a task based flow sheet there. And algorithm that is 1.2 here, in this case identification, what are the objectives there, identification of the PBS in the base case flow sheet, and to transform that task based base case flow sheet you have to consider that phenomena based flow sheet. So, that is why you have to transform that task based flow sheet to the phenomena based flow sheet there. And under this algorithm of 1.3 of this sub algorithm of set 1, in this case the main objective is to identify the desirable task and also phenomena based building blocks for overcoming the identified process hot spots there. In that case you have to also search the phenomena based building blocks search space there. So, this to be remembered. Also some sub algorithm also to be considered under this set 2 there. In that case that some objective like generation of feasible simultaneous phenomena based building blocks is considered, which are being used for combination rules there. So, in that case you have to use this algorithm 2.1, and algorithm 2.2 here a generation of a task based upper structure for identifying that feasible task based flow sheets to be considered there. And also an algorithm 2.3 here that identification of feasible tasks to be performed, and also in under this sub algorithm of set 2, here the generation of basic structure to be considered. Algorithm of to 5, in this case the main objective is to generate the task based flow sheets, and then sub algorithm this to 6, here main objective is to translate the basic structure into a unit operations there. So, these are the various objective under this sub algorithm of set 2. Now, what are those that set 1 algorithms for that? Now, for the application of set 1 algorithm, the following problems definition to be considered here, and in this case some given and also identify criteria should be there. What is that? Given a base case design and identified process hotspots that have been translated into design targets that should be considered in this case. So, that is why given as a base case design and the identified process hotspots to be considered there. And then after that you have to identify a set of desirable tasks and also the phenomena based building blocks that will represent this tasks. So, that is why you have to consider this problem definition before going to that using of the set 1 algorithms. And what are the step of that algorithms 1.1? In this case identify each unit operation, and after that you have to search that corresponding tasks from the database of unit operation versus various tasks, and then replacing of that each unit operation by single multiple task to obtain a task based flow sheet. So, these are the identification and searching and replacing, these 3 steps to be considered whenever you are using this algorithm of 1.1. Now, what are the steps of those algorithm of 1.2? In this case, for each task you have to find the corresponding PBBS, that is phenomena based building blocks, that will be from the database of tasks, that is versus PBBS, and then you have to replace each task with their corresponding PBS to obtain a phenomena based building block based flow sheet there. Here in this case it is given in the slides that according to that Babi et al. In 2015, that there is that reactor, after that there will be separation, and in this case task based flow sheet is the reaction task, and then that there will be separation task. After that phenomena based flow sheet to be formed based on this phenomena based like this mixing, cooling and reaction. Based on this there is called phenomena based flow sheet here, and after that you have to consider that based on this mixing, cooling, reaction, and how to separate those things by this flow sheet. So, this is the actually task to be converted to that flow sheet there. So, that is why for each task you have to find the corresponding phenomena based building blocks there, whether it is mixing, cooling or reaction. After that you have to replace each task with their corresponding phenomena based building blocks to obtain that phenomena based building blocks related or based flow sheet there. And then steps of algorithm 1.3, in this case also you have to identify that alternative tasks there and their corresponding phenomena based building blocks from the identified hotspots there. This is also again from the database that is known hotspots, task and phenomena based building blocks linked to that property ratio matrices of the binary mixers there. And then you have to add all those phenomena based building blocks to the original list of phenomena based building blocks there. So, this is the case where that identification of the tasks and their corresponding phenomena based building blocks is required at this steps of algorithm 1.3. Then what are those step 2 algorithms and what are those conditions, and also in this case of set 2 algorithms again that you have to have some that condition like given and identify what are the given a set of phenomena building blocks and design targets to be given there. And for the application of set 2 algorithms, then you have to use this a set of phenomena building blocks and design targets. After that you have to identify, and in that case what is that generate feasible sustainable design, and also that minimizes or eliminates the process hot spots and also satisfy the design targets there in case of that particular process synthesis. So, that is why as per set 1 also set 2 will have that this given and identification tools there. So, as per given you have to here that a set of phenomena building blocks and designs to be that considered, and identification in that case you have to generate the feasible sustainable design that will minimizes or eliminates that that process hotspots also, and also satisfy the that what are the targets of your design there. And in this case for the algorithm that under set 2 the first algorithm, you have to calculate the number of possible that simultaneous phenomena based building blocks. This possible this simultaneous phenomena based building blocks to be calculated based on that phenomena based n number of phenomena based building blocks. So, this equation here can be used to maximize the NSPB here for this maximizing problem. In this case that it can be calculated by summing up these phenomena based building blocks. If it is n number of phenomena based building blocks, then it will be here as n PBB minus 1, that is factorial, divided by n PBB minus k minus 1 factorial again k and plus 1, where this n PBB can be calculated based on this equation here, n PBB minus n PBB E minus 1 minus again n PBB m minus 1 minus n PBB D. What is this n PBB E? N PBB is the number of energy that is heating and cooling like this, and n PBB m is the number of that mixing, you can say that is phenomena based building blocks of mixing, and n PBD is the number of that phenomena based building blocks for the dividing. So, these are the things these are the parameters that you have to use to calculate this that number of simultaneous that phenomena based building blocks to maximize it. And from this total number of possible SPBS, that you have to identify the feasible SPBS. Now, among these SPBS you have to then segregate that which one will be the feasible SPBS using the predefined SPB building blocks and also combination rules. Now, after that what you have to do, that an SPB building block should be a predefined feasible SPB as is, or it can further be combined with other PBBs for the building blocks for generating more simultaneous feasible phenomena based building blocks there. Now, what are the rules of generation of feasible SPBS there? So, in this case you can use this SPB building block for the generation of feasible SPBS here. Now, here some inlet and some rule it is given there. SPB building blocks, if M and C, that M mixing and cooling will be used there, in that case inlet should be 1 to n there based on that that liquid, vapor or vapor liquid, and in this case you have to perform the cooling of a stream there. If suppose mixing based on the two phase mixing, what will happen in that case, your inlet again will be 1 to n there of that stream like this that liquid, vapor, liquid, even vapor, liquid there. So, in this case mixing of a stream with two phases will happen and to be considered also, and also here this like M is as reaction. In this case that again n number of that inlet to be considered, inlet stream to be considered here, like liquid, vapor and vapor liquid mixer there. So, in this case a reaction also to be performed without an external energy source, and then after that that a phase contact and phase transition. In this case again that vapor liquid and liquid mixer to be considered as an inlet stream, and in this case also you have to perform the contact of two phases for this that phase contact and phase transition. Again then phase contact, phase transition and phase separation, if you are considering as a SPB building blocks, in that case again here you have to perform the separation of two phases under this that inlet of vapor liquid and liquid liquid streams there. And what are those feasible then SPBS based on this SPBS building blocks? In that case, if we are considering that this M2, PSM, PC and PT, that means here mixing, two phase mixing and phase contact and phase transition there between this liquid liquid and vapor liquid phases. So in that case you have to perform the that mixing of two phases. And if you are considering that feasible simultaneous phenomena based building blocks for this mixing that reaction and cooling, then you can consider here that again liquid, vapor and vapor liquid as a streams as an inlet of 1 to n, and in that case the performs will be as a reaction with external energy source, that is called cooling. And if there is a mixing for the reaction, for two phase reaction, even phase transition, phase contact and phase separation simultaneously happen as a that feasible simultaneous phenomena based building blocks. In that case again that you have to perform a reaction, in this case phase reaction, phase separation under the stream of that liquid liquid and vapor liquid there. So these are the different rules based on that inlet and also that simultaneous building blocks, and several simultaneous phenomena based building blocks may form there, and out of which you have to select the feasible one of the that SPBS, that is called simultaneous phenomena based building blocks. After that the steps of algorithm 2 will be followed. Now in this case there are two levels to be considered here. In the first level you have to generate the task based superstructure. In that case identify the minimum number of separation tasks, and that will actually need to be performed, and sequence the tasks starting from all possible reaction tasks to separation tasks there. So in the level 1 that you have to consider these things, and in the level 2 you have to consider the merging of that adjacent reaction separation task, and also you have to update parallelly the task based superstructure there at this level. And what are the steps of then algorithms 2, 3, 2, 4 and 2, 5? They are in algorithm 2, 3 that you have to check the feasibility of the identified tasks through mixture property analysis, and in the algorithm 2, 4 that in that case identify the basic structure, and also in that case you have to make a list of that task as a feasible task with a corresponding basic structures also. And in that case you have to identify the basic structure, those will be able to perform a particular task. And in the algorithm 2, 5 after that you have to generate the task based flow sheets that will consist the basic structures there. Now let us have an example for these algorithms there. Now if we consider the reaction, if it is suppose exothermic single liquid phase where A and B react to produce the stream C there. So in that case the order of the boiling points for those streams, that is our components A, B and C should be considered in well manner, otherwise that whatever that mixing or reactions will be there, that separation of that byproducts will be very difficult. So you have to select that that components will be well different in their boiling points. So that is why boiling point sequence should be maintained in this case like this: A should be less than B should be less than C. So if it is considered, then you have to find out whether is there any azeotropes will be formed between those components of that A, B, C or not, because those byproducts whatever it will be coming, that may have that azeotropes, because these azeotropes may be they will have that similar kind of that boiling points after products. So that is also to be considered, whether the products will be forming any azeotropes or not. Now based on that algorithm 2.3 and algorithm 2.4 you can get this type of that task based superstructure of simultaneous phenomena based building blocks there. So here we are having this arc tasks and then S task 1 and S task 2. So if we consider that arc task, that is reaction task as here reaction, and S task as separation tasks, and again S task as separation task 2. So, if we consider that reaction separation both will happen simultaneously, then we are having these building blocks of that reaction separation. Now, separation may be between that A or B C, there will be a combination, there will be several possibility of that phenomena based building blocks will be there. Based on that, maybe either mixing, based on maybe either heating, based on the that cooling, based on the phase transition, based on the phase contract, like this. So, there may be a combination of like this separation of A, B and C, separation of B from the AC, separation of C from the AB, and separation of that A from BC. Along with that reaction also, if there is a pure that only if you are considering the separation and reaction separately, then there will be a building blocks. If you are considering reaction and reaction plus separation will be another building blocks, then you can consider it as R plus S, and S should be that again a different combination, like separation of A will be from the that BC mixer, and that B should be separated from the AC, and C should be separated from the AB, and like only BC may be separated and A should be that totally nullified, it will not come in the byproduct, and also AC may be separated and also AB may be separated from that reaction separation mixture. So, there is a combination of that operation and tasks there. So, here feasible and infeasible connections to be listed, and based on which one will be feasible, that should be considered. Now, from this you can consider that BC as a separation task and AC and AB, like this. So, these are the different that superstructure can be formed based on the tasks. And now, what are the different tasks that can be there? So, this here may be reaction and separation, maybe some other things are that extraction or distillation, even that extraction and also that crystallization, those are the things may come there. So, this is the simple example reaction as well as simple separation, which are being mostly actually happening in chemical engineering processes. Now, after that what are the basic feasible structure that are formed as per that algorithm 2-3, that you can form like this. Here reaction task, like that these are the building blocks to be formed for this task, and also here simultaneous phenomena based building blocks which will represent the basic structure here, like this. Similarly, for separation task and separation task 1, separation task 2, the corresponding that tasks are actually made here based on that that contact, and also that that other components also, what components is coming to that task and what are the components to be separated out, and based on this there are several combination of this that phenomena based building blocks to be formed, and based on that simultaneous phenomena based building blocks can be represented from this basic structure there. And after that, feasible basic structures as per algorithm 2-5 can be also generated based on this arc task, here reaction, and then desk task 1 and desk task 2, like this. Here separation of ABC, separation B from that AC, and separation of C from AB, like this. Here as task 2, here BC, AC and AB. So, these are the task based flow sheet which are feasible and sometimes not feasible, so that you have to identify or segregate the feasible basic structure as per algorithm 2-5. Now, what are the steps of algorithm 2-6 there? In this case, you have to use some database to translate that basic structure to task and then to unit operations there, and if the basic structure and its corresponding unit operations do not exist, then you have to generate a new unit operation there, and after that a list of unit operations to be screened up, and identify the feed stream based on that the phase identity there, and also the selected feasible unit operations are then highlighted in bold in table as shown in the next slides here. Here the feasible that here unit operations are shown here like this by highlighted. there are several that basic structure you can formed, and also from that basic structure you are identifying the feasible unit operations there. So, this one will be the feasible unit operations based on your total reaction separation process there as per process intensification. And also here this is also another feasible unit operations based on that identified basic structures there. So, these tables also you have to go through that what are the different that simultaneous phenomena based building blocks can be formed, and these building blocks based on the task on that here given different separation all those things, and also reaction separation combinations also there. And then you have to screening the feed phase and screening the structure, and also screening the that azeotrophs is there any formation or not. So, these are the case based on this table you can identify the unit operations there. So, I think we have discussed that preliminary based idea of that algorithms, how it can be used, and what are the different algorithms that are given based on that phenomena based building blocks, and also how that algorithms can be used by these that basic examples of that reaction separation, how this SPB can be formed, and how to segregate that feasible unit operations based on that algorithms. So, I will suggest you to go further about this algorithms. I think it will be very much useful if you follow this Juan Gabriel Segovia Hernandez these textbooks are there, chemical engineering design, optimization and control. These books will be very useful for this that more information of that stochastic algorithms which are being used for the chemical engineering process intensification. So, thank you for this lecture.